Okay, so one way of illustrating why you need a cross-training set is because you have to decide what is the highest point in the blue. And then you stop training, that is called early stopping. You stop training at the point at which this light green set here, the cross-training set, is optimal. So then this would not be the result for the testing set. This would then be the result on the light green set, right? That's the idea. I talked about the way to code the protein sequence. So here I show a window of 13 consecutive residues. For instance, residue 1 to 13. Or I to I plus 13, right? So you predict the secondary structure for the central residue. In this particular case, it's a P. The state in question, in parentheses here, is just to illustrate the secondary structure state. So this P happens to be in the state extended, so is the V before it and the F before it and so forth. And this is sort of the loop state or other state. Output is in fact a helix extended other. That's the hidden layer. Now, I said that every one of these 13 blobs here codes for 21 amino acids. So there's only 20 amino acids, but then there is one for a spacer. So that the proline can be at the first position. If the proline is at the first position of the protein, then there are 6 residues above it, so the ones before the proline here, that are not coding for an amino acid because at the beginning of a protein is nothing, right? So that's the 21st amino acid. Okay, so this is what is called sparse coding. Referred to as sparse coding because for every amino acid you have 21 units, 1 is 1, all other 20 are 0. Could you think about a different way of coding this problem with fewer units? So I have 21 amino acids. Again, mind you, 1 is a spacer and 20 amino acids. For simplicity, I have 21 that code for one particular residue, for one particular position in the protein. How could I use fewer than 21? Yeah?
We could use just 5 and use a binary coding with multiple ones.
You're a computer scientist. That is sort of one simple way of doing it, right? You could. That's one way. So you put it into 5 input units, and then you have a binary coding. Now, this is one way. Can somebody think about a way to use 1 unit?
Yeah, we can discretize some interval of values and assign those to units.
Yeah, right. You can put just a real value. 20, so let's just think about 20. It's easier for me to do it in my head. So from 0 to 0, 0.5, 0.05. I have to write it down. I'm stumbling over zeros. Can I write it down? Yes, I can write it down. So the A then would for A, the value would be some value between 0.04, or it could just be 0.05. The C would be 0.10 and so forth and so on, right? Not quite because we have 21, but I'm too lazy to think this through, to do the numbers. So we have 2 different codings, or 3 different codings. We have sparse, 1 unit, or 5. Now, can somebody think about value somewhere in between? It could be 5, it could be any of these numbers, but that possibly uses a little bit more expertise, if you want to call it that way. So these are all pretty dumb assumptions, right? The one that I show here are pretty dumb solutions. The one I show here with 21 is the dumbest thing you can do. You have 21 different units and you code it in 21 different states. Very simple. Put it into binary is also very simple. Put it into a real valued number is also very simple. Could you think about something that requires a little bit more expertise, so to speak? Something that you have learned already. What else could you do? But maybe more relevant for the problem. So we want to predict secondary structure. Any idea? No idea?
What about using embeddings?
A matrix?
No, embeddings, like word embeddings.
Oh, that's a great idea, but that is far away from trivial. That's a great idea. So just as Google does it, so or some protein vectors, yes, that's a great idea. I meant something simpler. And in fact, to my defense, so we're trying to set up a machine learning device, and this is some sort of machine learning as an input. So it's a machine learning to use machine learning. Fair enough. These days it's getting increasingly a plug-in library module. In fact, it does work very well. It's a great idea. But I meant something much simpler. I mean, to my defense of this, even looking up the library of word embeddings, to put this into a coding is much, much, much simpler, right? Something that is much simpler. You guys remember biophysical features? So there are some amino acids that have charge, they have positive and negative charge. There's some amino acids that are hydrophobic, some that are not hydrophobic, or hydrophilic is what they are called. There are some that are large, there are some that are small, there are some that are polar. And we could imagine that we put this into a vector, right? Now I just named 5 different features, biophysical features. So that would be back to the binary coding of 5. But all of these reduce from 21. How do you find out which works best? There are 2 ways people do this. One works and one doesn't. How would you find out whether it works? Which way? So, yeah?
If I want to find out which features are good, I can just train the model on them.
So try out is what he says. Yes, that's the way that succeeds. The alternative to just going ahead and training is to sit down and think about it. Usually that goes nowhere. I mean, usually you find a solution, what is best, but it may not be correlated with reality. The only way to really find out what reality looks like in this particular case is you have to try it. It turns out that the sparse coding that I show you is the best solution that I've come across. Somehow I sort of have influenced the field a lot in the beginning here of protein structure prediction, and maybe there would have been other solutions, not the word vector. That is a solution on a different level. But for simple encodings here, nobody has ever published anything that worked better than this simple solution, and that may be because I sort of biased the field a little bit too much by early on having said that nothing else works. I tried a lot. Yes?
Does it also work better than giving the network both the sparse encodings and the biophysical features? So
that's a great idea, and in fact the answer to that one is, so let me first repeat to you what he said. So the question is, what if I used both? The sparse and the features? And the answer to that one, so initially when I tried I did not have enough samples. Using them both worked worse. And any other system also worked worse than sparse coding. Since we have enough samples, using both works better. Okay? Where both is not the 21 plus binary, where both is the 21 plus biophysical features. So why does the sparse coding work better? Although it needs more input units, and I already said that initially when I did this first, I had not enough examples. Today, for this task, I said we have roughly 2 million. More than 2 million samples. When I started this for the first time, I had in the ballpark of 20,000. So that was really edgy for the system as big as I showed. I can't remember, I believe I had even 15 hidden units. So that was really, really edgy. Anyway, the reason why this works better, this sparse encoding, is because you make no assumption. So this in sparse encoding, all the 20 amino acids are independent basic vectors. Right? They are completely orthogonal to each other. All the 21 possibilities to put this sparse vector. The moment you put any of the other schemes, whether it's the real value, whether it's the binary coding or biophysical features, you introduce correlations between any vector used for any pair of amino acids. If these correlations completely reflect reality, then that's a good thing to do. If not, then the neural network or the machine learning device, whatever it is, first has to sort of learn this correlation, to untangle this correlation. And then it can learn how this correlation relates to secondary structure. And that turned out, I believe, to be the problem here. Another way of looking at it is, that is very related, is the sum of all these units here is 1. The moment you put it into the binary vector or into the biophysical vector, some amino acids have a higher sum than others. Okay, and that's the problem. Anyway, I talked about the balanced training and the unbalanced training. So in the unbalanced training, I take the samples in the ratio in which they occur in the database at random, but keeping the bias of the database. And what I get is a prediction that is much better for helix in red and other in green than for beta strand. If I now present in a balanced way at each training step one sample from each class, then I get a very balanced training and I give it a very balanced prediction that overall in terms of Q3 is less accurate than the other one. Simply because so this predicts all 3 classes equally well, but since most residues are in the class loop or other, the overall Q3 accuracy, so the percentage of residues correctly predicted in either of those 3 states, is higher if I get the majority class right. So this is why this is 60 and this is 62, but they are all equally predicted. And that in fact shows how you can use machine learning to break down something that made biophysical sense, which is that the beta strand formation is more local. So it's more determined, is less local, it's less determined by a window of 13 consecutive residues. But it turns out this is actually not true. The preferences are really as much for beta strand in a window of 13 as for alpha helix. Then I talked about how you sort of can make the average, yes?
Yeah, I have a question to you. So even though we are better, but with balanced training, detecting the beta strands, we're not seeing the beta strands actually from the window size, right? We just infer that it should be beta strands because we learned how dependent for the other are.
Yes. So the point is that I have my 13 consecutive residues, and I just take these 3 here. 13 is 3 now, and then there's my protein, and then there's my other beta strand. So this is further than 13 away. I still don't see that. My system, by training differently, by just changing the distribution of beta strands, alpha helix and and loop during the training, I have not done anything on this issue. So what that means, if I can train them equally well, what it means is that the preference for beta strand formation is already in this window, to some extent at least. And maybe just back to this argument that I briefly discussed before, so the top that we can reach is the top that we can reach, full stop, because the rest is somehow in the non-local part. We can still believe in this, and maybe it's true, maybe not, I don't know. And again, I will get back to that. But one thing is clear, in this local window of 13, the preference for helix formation is as strong as the preference for beta strand formation, which is why you can predict them equally well. The red is helix, the blue is beta strand. This is the number of correct, or the fraction of correctly predicted, and the red and the blue are equal. Beta strand and alpha helix are predicted equally well from the same local window. So for the first method for which I show the results here, incidentally this is not 13 but 17, but doesn't really matter. It still does not capture, so that's the important part of the question here. I still in this system do not capture the other strand. That is too far away. For 17 or 27 is still too far away. Everybody clear about that? Okay? So that brings us to this issue that length of segments are predicted not long enough, and for that I sort of stacked neural networks. So this is the neural network I showed you before, where in this particular case here is the 13 with the proline in the center and 3 output units, and now this, what the previous output is coming as input to the second level network. And you need, in fact, instead of 3 per residue for helix each EL, you need 4 because you need again a spacer unit, okay? So in this particular case here, I show for 3 consecutive residues, which means that I have 3 times 4 input units. In reality, I'm running the second level here for 17 consecutive. So I have 17 times 4 input units. Is that clear what the second level does? The second level is trained exactly the same way as the first level. It's just a different input. So the input to the second level is the output from the first level. They are not deep learning kind of methods. It's sort of the idea is somehow that you stack things up, but it's completely decoupled. In deep learning, you would have an algorithm that optimizes the whole system. In this particular case here, there are different optimizations. First, I optimize this first level. Yes? Yes?
Could you explain again why the first level has 4 red dots?
So the first level, again, let me repeat. The first level, and I should possibly put that closer as a slide. So here we have what I call the first level. The first level takes input amino acids and it gives output secondary structure. 3 secondary structure states. This is the input. Okay. This is the input to my second level. And again, the input to the second level here is, I break the way of showing it, this should be yellow somehow. And now, instead of 3 input units per amino acid or per residue, I have 4. Because at every single residue I need, again, a spacer. Just like before, I had 20 plus 1. In this particular case, I have 3 plus 1 is 4. Okay? So this is why here I have 3 times 4 in this figure that I show. Yes?
I just have a question about the spacer. Wasn't this element supposed to be at the beginning?
Yes.
Protein.
But now, so you have to imagine, again, so the spacer, let me repeat this point. The spacer unit is, if this is residue 1, 2, 3, 4, 5. So if I had just a window with 3. So the window with 3 here, that's the central in this particular case here, and then there would be a -1 unit. That's the spacer, right? And previously this was the spacer unit on that end, and on the other end 2. If I take the last one, I have the spacer in the other direction, right? For 13 I have 6 spacers. So here I would have 1 spacer for 3 input units. Now why do I need a spacer again? Because again, this system here, the second level, is run as a window through the system. So this second level network will at one point use the first residue in the protein as the center of the window. The center of the window, in this particular case here, really is shown a window of 3. The center of the window would be the P here. And if the P has to be the first residue, again we need, before it is spacer residue. That's why we need 4 input units rather than 3 input units. Yeah?
So I train the first level network and then do the predictions for each of the amino acids, and then I update the predictions with the second level network.
Yes.
Based on what the neighbor predicted.
Okay, so let me repeat that and slightly correct that. I said yes to you, it's not quite. So what I do again, I run my first level, completely predict secondary structure for the first level, and that's the secondary structure prediction method on its own. Okay? Now I sort of try to refine that. My second level network, I hope, will learn things such as H, LH, LH or something like that doesn't exist. There must be, helices must have a minimal length. And the way to learn that is I teach the system the local correlation. So I train again. And in this learning local correlations, all I put in is the predicted secondary structure of the first level. That again has been trained on the same split of the cross-validation set. Okay? And so this one is done. And now I put this into and train again. Same split, everything the same as before, except the input has changed. Yes?
Does it help the second network to still get the amino acids as input, kind of like in ResNet?
So the question is, what if would it not help to put the amino acids back in? So rather than having 4 input units, you could imagine to have it 3 plus 20 plus 1, so 24 input units. Yes, in fact, that is better, but I'm not entirely sure whether it's better on this level. So I haven't tried that on this level. I will show you something later that does exactly that. Yeah?
The weights for each one of the amino acids here, like for the first level network, this is shared weights. This is like the same network.
No, they're not shared. Well, I'm not entirely sure. So yes, they are shared weights between the V and the P, if that's what you mean. Yes.
So
this is there's one device trained, and that same device is just running through. So this is the way you run this. You run when you put the window through the protein, it's the same weight. So so when you train, you sort of every single time you move on, you retrain, right? Once the device is trained and you test with it, then you just run one device without changing anything through that protein. And that's in that sense here. That is the same device with the same. He calls it shared weights, identical weights. Yes.
Okay, did you try, for example, like having 3 different networks on the first level and then training this from end to end? So instead of like training.
No, I've never tried that. So I would have to think this a little bit through. Let me just repeat what he says. And I never had this idea. So the idea was, well, I bring in the same network here, and I have defendable reasons for that, but he says, well, why not slightly altering that? What I could imagine is that, in fact, the 3 here differ. I immediately see some problems because you want to learn correlations, and maybe the other one doesn't have the same correlation because it's a different network. So you want to see something that goes wrong on the first level. But to, in fact, put sort of different networks on the second level, that is a great idea. Again, I'll get back into something like that later, on a slightly different level. But the idea is clear of the second level. The second level, again, has the same output. It refines only what the first level does. And it refines, as you see here, the first level predicts on average beta strands that are 3 E's long, helices that are 4 H's long, while the second level makes it much longer. And for comparison, so this looks much more like the observed levels. And this is also true when you look at the distributions here. Red is the distribution of the segment length observed, blue is predicted. You see throughout, and this is just number of segments here of helices, beta strands and other, and you see that really the blue and the red are very, very similar. So the entire distribution is somehow similar, yes? So the question is, well, so the question is, what's the reason here for decoupling these networks? The reason is history. The fact is, when these networks were trained, nobody had ever done anything like that. Okay? This is 25, 26, 27 years ago now. So the idea of a coupled, so what you now know as deep learning, didn't exist. Now, having said that, I would still defend that the simplicity of the device here has some advantages. Deep learning works very well if you have enough samples. And clearly, this was not an example where we had enough samples in those days. Today, we are redoing this. Today, we may have enough samples, and ultimately, we are working on it in our group, and at some point, maybe I can answer your question, whether it does work better to sort of train it as in a convoluted network type of way. Okay, so here is a slightly different way of doing it that goes back to Gianluca Polastri. Ultimately, the idea goes back to Paolo Frasconi. So this is a network that is a recurrent network that goes back into itself. So in this particular case, again, I briefly showed it. So now what I showed you before is a 90-degree rotation of this image here. So the output now is on top, not on the side anymore. And the input is at the bottom here, not on that side, on the left side. And what you now see is that the output from the first level is put back as an input into the second level. So here is a device, the recurrent network couples the training. This is still not deep learning, but it's a network where the output is fit of the same position while it's being trained, fit back into it. Okay? That's a recurrent network, and it in fact does work very well and has a similar, just a sec, has a similar success. It makes helixes be predicted longer. Yes?
The first network. Will it make a difference since we are giving input as secondary structures? So will it help if we use different activation functions for the second layer?
So that's I do not repeat this question because you're sitting in the back. I do not know whether it helps. What I do know is I tried a bunch. So when I did this, people argued about different activation functions. And in fact, different shapes. I can only tell you whatever I tried didn't work better. Maybe there is another one. So again, when I did that initially, I came from the field of neural network and I tried these kind of things. It didn't work for me. But I cannot answer your question. Okay. And this again is the answer not for the recurrent network here. That was the answer for the network I showed you before in the first and second level. But the major problem here is we've solved two problems. Segments are longer. We solved the problem that beta strands are predicted better. But the problem still is prediction accuracy is not much above 60%. Okay? So this device that we now created with machine learning, in fact, is slightly better than anything else that exists, and it does beta strands better, and it does segments better. So this is already great, but it's not good enough. We want to do better than that. And in order to be doing better than that, one thing is clear: I have to put more data into this input, more information into the input. How could I do that? Thank you. Kudos. That was a first in this setting. That was an absolute first. So I've given this lecture a couple of times now. Did you know this? Is this sort of related to the sun? Did anybody else guess that? I mean, it's easier to say now that you guessed it anyway. Okay, I have to repeat it. Can you? So how do I get? Since you didn't hear it, the question is still standing in the room, right? I guess that this side in the local vicinity hasn't heard him. So any idea how you can put? So this is a great proof that it's not trivial. How could you put more information to the system? And I still so. Anybody who has not heard the solution, feel invited to guess. Yes?
Measure more proteins?
Use more proteins, yes. So the problem very often when you do machine learning, in particular in computational biology, is you're very greedy for getting whatever data you can get. So when I did this for the first time, I used just anything that was out there. So now the idea is get more data. Yeah, but was not available at the time. And again, if I read it today I have much more data. But in fact, it turned out that the more data itself is not enough. We need a better trick. But anyway, so my point is, most often when you do machine learning, the statement "I need more data," again and again, we published many papers over the years in which this was the most limiting step. And sometimes we could actually show in a later paper that was the most limiting step, the lack of data. But usually you have to find a way without that, because you don't have more data. So how can you put more data into one window, yes?
Can you create artificial?
Yes, so that's a great idea. But unfortunately it didn't work. So the idea was maybe we could create artificial input, and it works in fact for image analysis very often. There are many applications of deep learning where sort of simulating data helps you tremendously. Now, the reason why it doesn't work here is because whatever we can simulate is on a level of performance that is around about 60%. And we need to get higher. We need to put something in there that allows us to sort of climb on the ladder. And anything that I can simulate is below where I want to get. Yes?
Maybe we could try to get more useful information out of our data, so using any kind of attention or memory mechanisms for our networks.
Detention?
Detention mechanisms, like to weight different regions of the input in a different way based on previous experience, previous sequences that we have seen.
Well, if you think about it, so he says, let's put a different weight on different parts of the sequence. So that could be, for instance, I put a different weight whether you're in the beginning of the protein or in the end. That is the idea, and in fact that already works better. So that is an interesting idea. I'll get back. I'm not sure whether I'll get back to that. But that in fact turns out to be a crucial idea for some other gain. With that you gain something, but you're not really pushing the 60% number. You gain something else that is again very valuable, in particular the marking of where you are in the protein sequence. And I'm not entirely sure that, so there are a couple of things related to that, yes?
So I didn't only meant depending on the position where we are in the sequence, but that the network decide about it, so on what we have seen before.
But isn't that exactly the same thing as the second level? So this is why Shannon Zinovsky, so I glossed over it today. So this idea of a second level network had been invented by Shannon Zinovsky in '88. And Shannon Zinovsky, in fact, they had introduced this idea of a second level network, I believe with something like what you say in mind. That there is a second level that learns from what the first level has prioritized, and therefore it would improve accuracy. That did not happen at all. This is why the idea of a second level fell through, because it didn't help. But it didn't help, so they never realized that it helped for something totally different. Yes?
Yeah, but we're still restricted by a certain input length, right?
Yeah.
So when we have some kind of memory in a recurrent neural network, for example, we could make sense out of longer input sequences.
So now that is, let's just go into that story. So one simple answer is make the window longer. And this is what many of us have tried for many years. And ultimately, so I talked about a window of 17. Why not make it 50? Why not make it 80 or something like that? Why not take something that's almost the entire sequence? You cannot take the entire sequence because proteins vary so much in length. You have to pick something that is sort of common to at least most proteins. Otherwise you get very strange effects. But 80 is some number, or 100 is some number. The longest that was tried, I believe, was about 50. And they didn't work. And ultimately, the explanation why all of these longer windows didn't work is because the longer you make the window, the more information about what is important you introduce. But what the problem is, the noise increases too. So as long as the data set is too small, what you add is more noise than signal. And this ultimately may be behind this issue here. Once we have enough data, so if I pulled in enough data, then I sort of would overcome this noise issue. And clearly, when I tried again with a database that was 30 times bigger, and then already I saw that much longer windows were supported by the data. So maybe today even bigger. But there is still something you can do before. How can you put more information into one window of 13? And the answer that was given here is, why not use a profile? And let's get back to this graph that I showed you before. It shows the number of residues aligned versus percentage sequence identity. Up here, every pair of protein has a similar structure. 100 residues aligned, 33 are identical. These two proteins have the same structure. And now comes the point that I've maybe not spent enough time on in this class. Now, let's turn this around. You have 100 residues aligned. If more than 33 are identical, these two proteins have a similar structure. So that means 67 can differ. Okay, so we have a 100 residue long protein. 67 of the amino acids can be changed. So for 67 of the positions, I can flip or change the amino acid against another one. My question to you now is, if I chose at random 5, not 67, 5, what do you believe is the probability that the structure will be the same? Is it high? Who believes it's high?
Low.
It's low. So who believes that the probability that the structure will change is high, or that with 5 random changes, most likely you will change the structure? Who believes that? You should all raise your hands. If you want to believe the same thing as I do, then you should all raise your hands. So most changes are not neutral. Most changes will affect structure and function. 5 random will change. So how come that 67 can change and I say 5 random will make a difference? How can these statements be true at the same time? Any suggestion?
Maybe the areas where they're changing a lot are not random.
Exactly. And in fact, there is a selection criterion. There's a selection mechanism. There's something here behind it that in fact selects for the extremely unlikely situation. The extremely unlikely situation is that you have 67 in 100 changes without changing structure. Extremely unlikely. But it happened in nature. That's what evolution does. Evolution selects what works. If it doesn't work, it doesn't survive. We will not see it. What we have in this graph here are the, let's call it survivors. I mean, I'm using a very, very misleading technology, but words, very misleading words here. Ultimately, what we have are the pairs of proteins that do the same thing. If the protein remains to have the same structure, if it does the same thing, then the protein is sort of doing the right thing and the organism survives. And we observe it. If not, it disappears. Okay? That's why most of the changes that lead a gas, that lead somewhere where it doesn't work, we do not see. We only see what works. And that is a very tiny subset of all the possible space. This is absolutely not random. Okay, this means that if I now looked at the particular changes that are possible in that family, then these changes are relevant for structure and function. So the example is this family shown here. Is one particular protein family, and there are 4 residues, 1, 2, 3, 4, slightly marked by colors, that are largely conserved in this entire family. So this is over 60 residues long, and only 4 positions are really most important, 4 of 60. And this is where they are. They're not randomly distributed. It's those 4. And those 4 are the key residues for that family. And you learn about these key residues for that family once you build up the family alignment. Right? When you look at these 4 key residues, you see that the first here and the last, they happen to be next in 3D structure. The middle ones here are also next to each other. Now evolution acts upon the 3-dimensional object. Whatever it does here has something to do with what is here. So whatever changes you observe here have to do with what changes are here. Or put it differently, if I took out a window of 5 consecutive residues here, in this entire profile, in this entire family, I see something that is happening elsewhere. Because these 5 here are constrained by what happens here, which in sequence space is far away. Okay? In 3D, those 2 positions are together. In sequence, they are very far away. They are sort of coupled. They are coupled because they are close in 3D. They are coupled, and you see this couple in the family, in the alignment. in the profile at that position. So this is a little bit like the raindrop. You take a raindrop, in the raindrop you see the world. And this is like that too. Because in the 5 consecutive that you cut out here, in the pattern of change that you see in those 5, you implicitly have a signal from something that is somewhere else. So that is the world, right? That's the analogy. Another way of analogy is you transfer a problem that is sort of chaotic into a problem that is well solved. And I should have explained this chaotic problem a little bit longer. But anyway, so the way you do that is just like before, except for, I'm sorry, I changed the coloring here. So what previously was yellow is the 13 input blobs, here is now reddish or orange. That is the same thing here, except for now what we see is this is the protein, and here is the alignment of 1, 2, 3, 4 proteins. So again, it runs from residue G, it's not the first residue, but say the 5th residue, 6, 7, and 8, and so forth. And that is sort of the central window here. And that now means that at every of these input windows, you no longer have 1, 1, and 20 zeros, but you put in the frequency of what you observe in the alignment here. So in this particular case here, it's always D. In this particular case, it's always P. And then here you have 2 E's, 3 A's. So you put in the probabilities. That means you now have replaced the sparse coding by an actual real valued number that is simply the frequency in the alignment. Clear? Now the system, in some sense, is what you said before. It is like a memory of regions that are more important. But that memory is taken from the alignment. That memory is taken from, in fact, the evolutionary fossil of what is relevant in the protein. We take the multiple alignment as a record of this space of possibilities. Okay, that's technically it's very simple what you do. You just, as he said, you just replace the sequence, the sparse coding, by a profile. Technically it's very simple. But it works because, in fact, the profile is a printout, if you want, of where important regions lie. What change where change matter and where it doesn't. What works for that particular structure. So it's very, 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 what doesn't for that particular structure. So it's very informative about details of particular proteins. Okay? Is that part clear? So it's the same specific information. Remember we talked about the blossom versus the profile. The family-specific profile versus the generic exchange blossom matrix. And I said that the generic blossom matrix is better than pairwise sequence identity, but it's always worse than the profile that you take from a particular family. And again, the reason for that is that the way evolution works, what you see are things that in fact are working. Now if you randomly created proteins, these families here would be containing no information. They only contain information because of the evolutionary principle. The evolutionary principle being that whatever doesn't work is not observed. And whatever works typically is the thing that is neutral with respect to structure change. So has the similar structure. And that is why all of these things that we see here, whatever we see at that position, whether it's a D or N or Q, they all will still be compatible with having the same secondary structure at that position. And that means that as an input here, you now, instead of 1 being 1 and everything else being 0, you can say, well, here in this particular case, 3 residues are possible. And you can specify the probability if the alignment is large enough. And that, in fact, is a much more fine-grained way of predicting secondary structure from sequence. Any question? Yeah?
Do we feed just the protein once to the network, or do we also feed each of the alignments as well?
So now the question is, in fact, that again is something that is not quite clear from the start how you do it. So you could do this in 2 ways now. You could argue, okay, I put in the probability vector here into my system, and that's the input. Alternatively, I can say, well, what I have here is 1, 2, 3, 4, 5 different proteins that I know have the same secondary structure, and I could train them separately. So I could, for each of these 5, use sparse coding, as I did before, but I now, instead of training for 1 protein, I would train with 5. And then you can ask, which of these 2 performs better? Is the alternative clear to you? Is anybody not getting what the second alternative is here, or second idea is here? Yes? So again, so in the first idea, I take my alignment here and put in the probability vector as input to my device. Okay? That's the first idea. That's the one I presented. Now comes a new idea. Well, ultimately, why not go back to what we had before, which is sparse coding? And with sparse coding, I have 1 protein for which I can train. But since I actually have an implied, in the alignment, I have an implied secondary structure prediction. So I assume that all of these 4 sequences here have the same secondary structure as the first. So I could just take them and retrain on every single one of those. Not probability, stick with sparse coding, but instead of training only on this one here, as I've done so far, train on all 5. Again, assuming that they all have the same secondary structure. Okay? So then, in one case, I would sort of learn by putting the probability vector in. In the other case, I would learn by just having many more examples. And in these many more examples, again, my system ultimately could learn, since in these 5 cases it will, for every single one, see again that here at this particular case, it can be D, it can be N, it can be Q. Because it will see the same case with a Q and with an N. Yes?
You said we have many more examples when we also fed the other alignments. Why didn't we fed them in the first case?
Well, so it's a little bit unfair. So yes, we could have done that before, but I could have phrased. So my question before, how do I get more information into the system? Now you say, well, I could have rephrased that question and could have said, well, I don't have enough samples. How do I get more samples? And ultimately, that is sort of the same, or it's actually not only more samples. It's also, yes, I could have done that at the first place. And my question now is, what do you believe will be better? So why did we not, let me answer your question in a different way, and let me also answer the question that I just posed. It turns out that putting the probability values in is in fact better than retraining with a sparse coding with more samples. So why did we do that before? Because it works worse. There's another way of answering your question. But in fact, historically, again, I did the profile first, and then I suddenly had the same idea that you came up with, and I tried it only afterwards. Why didn't I think about this one first? I actually don't know. The other one came to me first. Because most likely, I always thought about probability when I saw these alignments. But then, whatever, so it works worse. Yeah?
You mentioned that if you were to use the multiple sequence alignments as data for sparse matrix, you get 5 times the data, 5 times the number of samples. Is there a reason you couldn't do like a walk through potentially 2 sequences together and kind of artificially create some third one that doesn't exist in nature?
Oh.
Probably has the same structure.
Oh, so that's an interesting question. So that's a very interesting question. And today I have only 52 slides and I still don't get through. So this name here, Michael Bodden from University of Queensland, Brisbane, is crossed out. I'd hoped that Michael, who's currently visiting in our group, gives a talk, but unfortunately he doesn't have the time. So Michael, one of the things that he is doing is he is trying to take multiple sequence alignments and guess what the ancestral sequence has been. So he takes the multiple sequence alignment, and I'll just put up the name so that you can see it there. Let me find my slide again. So he takes the alignment and builds it onto a tree. So in the tree, so there's he has 2 protein sequences. So the family, in this particular case here, would have a family of 5. 1, 2, 3, 4, 5. He puts it on a tree. And in the tree, for instance, these 2 are the closest relatives to each other. And now the question becomes, for those 2 I know the sequence. Say it's the first and the second here. I know the sequence. And my guess is, or my question is, what is the most likely ancestral sequence of those? Again, we don't know it. We don't know, we have to guess what the organism was that was the ancestor, but the organism died out, we don't have the protein sequence. So now we can guess the protein sequence. So we can simulate a protein sequence that is the most likely ancestral sequence. And therefore, we can ultimately, what he's doing is the entire family. What is the most likely ancestral sequence? So he does that completely computational, this Bayesian network probability theory. And then they come with a most likely ancestral sequence to protein families. This is a particular enzyme where the ancestor here lived 200 million years ago. Okay, so this is a long time ago. Then they take this ancestral sequence, they put it in a tube, and they see what type of feature it has. For instance, is it still an enzyme? And if it is an enzyme, what does it do? And this is a technology that is becoming increasingly important for protein design, for all kinds of processes, from food processing to biochemistry, chemistry, to processing oils and other things. So this is becoming increasingly relevant. And now the question could be, well, this creates a set of possible ancestral sequences. Why not use them all? Ultimately is the question here, to bring more samples and simulate how the entire space would look. Would that not improve? I believe it's a great idea. We just put that in as a grant. So we don't know the answer to your question. But I believe it's a great idea. Okay, so this is totally cool. This is a totally cool technology. Okay. Now, so this is the single sequence, we put the alignment, and the remainder of the story is the same. So what that now, if you want to do the whole process, what it means is you have to begin with a sequence for which you want to predict. You align it against the database, you somehow find the ones that belong to the same family, you extract the alignment of the profile, you put that into a system of first and second level, and then you predict secondary structure. There are some additional features of the final system. So the final system uses some additional input information. For instance, it uses where the current window is with respect to the beginning here and the end of the protein, how long is the protein, what is the overall composition of amino acids. So there are some additional features that go in, and all of this, there's a first level and a second level. And then comes this issue that I also did not talk about before. I said that the balanced training gives 60%, the unbalanced gives 62%. Now I have 2 different networks. One is better at sort of giving a balanced result, but slightly worse overall. So these are different solutions, and this is also an idea that came up here as input to the second level. Why not use differently trained solutions? And there's a theoretical statement that these are, you want to separate a device that separates the red from the blue. These are all lines that do a good separation, the gray lines, and by simply averaging over those, you actually do better, as long as there is some white noise, what physicists call white noise. White noise means some problem or some mistake, some error in your prediction that is not systematic. Okay? So as long as each of these gray lines has some part that is not stemming from a systematic error, an average over the gray lines will always, shown here in green, will always do better. And this is in fact a way to use several different solutions by just averaging over those. And then comes, what about, we put also the other question was, we put some of the input into the second level. So what this image shows there's a third level where you put the predicted secondary structure and something else that I will briefly talk about in 2 lectures from now, solvent accessibility. We'll all put that together with input and predicted. So this third level now gets the predictions from the first level of secondary structure, solvent accessibility, and gets the sequence back in. In fact, that's not well, yes, it's shown here. So this is then this third level sort of has the large input of everything. And that's sort of the device we use. Now, when we look at this particular example here, one particular protein, what I show is the amino acid here from residue 1 to 67. The observed secondary structures, beta strands mostly here. Here's a piece of helix. That's the typical example of the first generation method, Schau-Fassmann. This is the second generation Gore, and that's the method that I show. Now overall here, this is 59, this is 65. I said on average here, the first generation is 50 to 55, so this is higher than average. And the second generation is sort of 60 roundabout, so this is higher than average. This method that I showed you that uses the profile as input gets a performance of 72%. And for that method, this was roughly average. So this is a number of protein chains, this is the distribution, 72 is essentially where the average of this distribution sits. And this is an important 72.3 to be more precise. This is an important statement here. So what this shows is your performance per protein. And there's a difference between proteins. Why? So some proteins, let me point that out to you, are predicted at levels. So this is the best secondary structure prediction method that existed at the time. So today I showed you one of the ones that are better. But even these devices, for some proteins, they do predictions that are worse than random. The random is 30 something, 35. So these three are all below random. So there are 3 proteins in the data set. I can't remember how many proteins, 600 or something. It's not written on the slide. I believe the sum over all the green is around about 600. In 600 proteins, there are 3 that are predicted by this device at levels below random. Okay, some are predicted also completely correctly. 1. But anyway, so why this spread?
Because some proteins behave contrary to the others.
Yes. So I can be very, very not nice now and say what he said. So to repeat his statement, he said, so why are some proteins predicted worse than others? Because some behave worse than others, is the answer. And it's true, but it's sort of circular, right? But ultimately, I do not give you much more than that. So one way of looking at it is, so now what you do, when you ask yourself why you make mistakes for some cases, what most people who develop methods do is they look for some features in these proteins here. For instance, the feature could be, well, I know that profiles help me a lot. Maybe some of these proteins here have no profiles, so they have alignments that are tiny, so they have no family members. Okay? Say, in this particular case, this and this is not the case, but for one of those here, this in fact was the answer. Bingo. I have explained why this performs poorly. This one here is an extremely, so it's a cold shock protein that makes fish in Arctic waters survive without being frozen. It essentially prevents the blood from being frozen. So it has very strange features, that protein. And in fact, even doing the structure is very complicated. So strange features, argument number 2. So if I did that, is that a correct way of explaining why my method didn't work for those cases? What is it that I'm doing wrong here?
Maybe choose a few examples.
Yeah, well, that's what I did, right? So I went one by one. And I essentially explain why this, why that, why that. That is like picking examples. Is that what you meant?
Like the proteins that I used to train my model, and few of those proteins, for example,
Yeah, I take all of these. I take them one by one. That's why there's a name on top here, because I actually look at every single one of them. And then I explain why my method doesn't work. And again, 95% of all the method developers do this. This is wrong. Can you explain to me why? Yes?
Because it's more like pseudoscience. I think in this case it would have been more helpful to do an outlier analysis where I could see, I could do something like a PCA or something where I could see that these features have, the features are vary more than, let's say, 95% of like the data that we have.
So I'm not entirely sure how to translate what he says, because I'm still not quite sure what he says. But let me turn this around. So you begin by saying this is pseudoscience, right? That's a very, very true statement. But why? Now you say you ought to pick features of those, more rigorous features. No. So the first step, in fact, I say that one of those here, I can't remember which one it is, I believe is this one here. One of those has an extremely small family. And I know that the profile is relevant for getting a good prediction. So if the profile doesn't exist, then it will not work as well. I know that. But in order to do this, lift this from sort of a statement from pseudoscience, which I did now, to a statement of science, I have to measure. And measure is, in this particular case, I have 2 members in the family, say, right? Now I have to look at all the others for which I have 2 members. And if all the others for which I have 2 members, provided I find others, so again, if I find no other example, then it's complicated to make an argument. But if I find 5 others, and they are all here, then I elevate it from pseudoscience to science. If I suddenly see that the 5 others are somewhere here, then the explanation is wrong. Yes, on average the profile helps, but that is not the explanation why this one is so low. This is why on average proteins with no profile are lower than proteins with profile. That I can say, but it is not why this particular case goes wrong. And this is ultimately what we have to do in order to make it a scientific statement. I have to formulate whatever I believe here as something that I can measure, and then I can compare to other proteins here. Most of the time this doesn't work. And most of the time that leads to the point, well, the point is I cannot easily improve my prediction method by just seeing what is going wrong. If, and that was the second part you said here, if there were some feature that you could see which goes wrong through some, not support vector, some PCA you said. I look at the feature, the input features, do some principal component analysis, and try to see what of the features that I capture makes sense and what doesn't. Ultimately, if you think about this idea, then what you do is you replace the neural network by a PCA. And it may work, and it may not work. In this particular case here, it didn't work because the neural network extracted features on a level of complexity is much higher than a PCA. So I tried something like that. So you couldn't improve by picking out features that didn't work on that level, because the whole device had extracted a complexity level. Yes?
There was something I don't remember precisely the name for it, which is that would do like outlier analysis. And that will tell you the relationship between the samples within, like the features within a set. So if I have 10 features, then you could see how each one of them like correlate to that.
So if you're lucky, the statement is there's outlier analysis. And let me repeat one point. I can't remember. You said that you always should look at the explicit examples, and you always, whatever you do, look at the outliers. Very often outliers are things where you're programming, very often with outliers are things that help you find programming mistakes. If you don't find programming mistakes, you will always learn something from looking at outliers. And sometimes you can sort of look at group features of outliers, do a common PCA for outliers, and somehow stumble over things that you can then really use to improve your method. This does happen, yes?
Could you explain again why exactly we have this variation?
So again, the question is, can I explain again why we have this variation? And ultimately I said I cannot explain why we have this variation. It is true that that some proteins have much simpler structural features, are somehow more generic than others. And it is certainly true that many of the ones that are down here are proteins that have features that are completely unexpected. And so many of those here, some of those in fact were also structural mistakes, it turned out many years later. But some of the variation here comes from proteins being in extreme environments. So they are exceptional proteins. Some of the variation comes from the fact that proteins have very different lengths and the structure formation is defined to less or higher extent by local interactions. Right? So some proteins are more fitting to completely defined by local, and some are more defined by non-local interactions. And that ultimately has to do with the size of the protein, the environment, and their function. So ultimately, I'm saying I cannot explain the spread. Just don't get that wrong. I'm giving you a couple of sort of motivations for the spread, but it's not an explanation. Yes?
Was this analysis also done for the positive outliers?
Yes, in fact that is exactly part of what you immediately have to do in order to elevate it from science to pseudoscience. But typically when you look, you ask, how can I improve my method? So your first question will always become, what went wrong? Yes, it was also done here. And again, there's not much that we have learned so far from doing this. And there's a lot of work that went into it. But here's something else. And I'm missing a slide. Okay. Well, okay. One way of yes?
The algorithm in the end predicts probabilities and structure. There is helix and beta strand. Did you look how sure the algorithm makes its prediction with these outliers?
Okay. Thank you very much. I have a great room today. So he predicted the next slide, and this again is an idea that I find very, very crucial. And you're the first, so we have two firsts today. I'm impressed, guys. Thanks. So far I have a device that has 3 output units, H, E, L. And the prediction is whatever is the highest of those 3 units. Here I show you 2 predictions for 2 different types. And one, H is 0.5, E is 0.4, and L is 0.1. Again, it does not have to sum to 1. Just create the sample like that. My second prediction, it's H 0.8, E 0.1, L 0.1. Both of those would be predicting H. Both cases, the H unit is the highest. But you see that the second prediction here, the probability for H is much higher than for the first. Yes, the first is an H, but in the first one here, H and E is almost similar. While here, the H stands out by a factor of 8, at least compared to the second best. Or has 80% of the signal, 0.8 of the probability. Now, you could ask, maybe, if the decision is stronger for the entire protein, maybe then the protein is on that side of the distribution. And if the decision is weaker for the entire protein, maybe it's on that side of the protein. And this is what I show here. It's the strength of the prediction for an entire protein. So proteins with very strong predictions, so this type are here on that side. Proteins with very low probabilities are on this side here. And this is the performance per protein. The blue is just a fit. As no, the blue doesn't quite fit the data there, but you see that there is some increase. So if more of your residues are predicted with a high probability, and that ultimately gets back to the same question, why is the spread so large? So if more of the residues that you encounter are like the generic structure forming residues, that means they are more on that side here, then the entire protein is more on that side. So on this side here, the red is higher than on this side. Right? Everybody gets the idea? I'm not saying it's 100% fit, but on a per residue level, the fit gets much better. And the graph that I want to draw your attention to really is the black one here. That's the percentage of residues, there's a typo here, predicted, and that's the performance here. So let's begin at this point. When I predict for every single residue, so I force a decision. In the case that I showed you before, the H was 0.6, 0.5, the E was 0.4, and I still force a prediction. So I force for every single residue, then the performance is round about 72%. If I now pick the 50%, so here's 50%, the 50% of the residues for which the difference between the top and the others is highest, okay? I just picked 50%. So 50% is here. Then for those 50% of the most strongly predicted residues, performance rises up to 88. Okay? So the strength of the prediction, the probability of the prediction completely correlates, almost a straight line, completely correlates with performance. Again, the strength of the prediction is not something for which you need to know the structure. You have for every single case that you will predict tomorrow, you will have this strength available. You can predict this strength. And so here shown is a value, a reliability index from 9 high to 0 low. So this is what users can use to in fact zoom into the most strongly predicted residues. And that's an immensely strong vehicle, and as a developer you have to make this available. You have to create something like that. It will not always look like this. In fact, this is a lucky case where we have many cases where this is almost linear. This has worked very well. We have many cases where we have to do much more and renormalize in order to get something that is almost as useful. This is just a good case. But as a developer, you ought to look at this probability and ought to give that to users as a feature to use. It can be very strong. And I believe with this, I leave it for today. Yeah?
The RI is computed on the output probability.
Yes. The RI here is essentially is a simple difference, or it's simply taking the probability in the scale so that you get an integer between 0 and 9. It's a very simple scale. Again, the RI reflects the strength of the prediction. So in this slide before here, this is strong. This is a high RI, this is low, that's a low RI. And I cannot quite remember the exact definition, but I believe it's just the number by 10. So this would be, this most likely here would be an RI of 8. So most likely what I showed here is this example. Thank you very much for your attention. See you on Thursday.